Oops. So the goal today is to make as many connections as possible. And asking these questions that are far-fetched is really good to ask. Because that's the thing with learning. Whenever you're learning new things, it's not just you trying to okay, how do you think memory works? Okay, I'm getting sidetracked, but I learned more about this recently. So there's this sort of assumption that people think
Long-term memory.
we'll forget about long-term memory. We'll forget about the duration, short-term, long-term. We just think about memory in general. But that is something for sure. I'm not saying it's not, but it's not as relevant to this point.
Significance.
Yes. But actually, let's go with the super simple model. Like, there was an assumption before that memory is just like a box, and you just need to put more things into it. So if you learn this now, you'll be able to just use it because you just store it. It's like stored in your brain now, right? It's like you store it into the computer. But that's not how brain works. Our brain works by connecting things. It's like a network. When you form something, you connect it to something else, right? And you might get something new that doesn't connect too much to it. What do you think our brain's going to do to that? Why would that be deja vu? Deja vu means you. Anyway, doesn't matter. But it's like, let's say you just see a random number plate on the street.
Mm-hmm.
You're going to forget it by tomorrow, right?
Mm-hmm.
Why do you think that is?
Because it has no significance.
Yeah, we don't care, right? Yeah. Yes, sorry, yeah. I think I was agreeing with you, but yeah, I just wanted to bring the bad model first. But yeah, you're definitely right. Significance, right? It's not relevant to us. So, I mean, that makes sense, right? Because think about this. We're seeing so many things. We're processing so many things. Like, we see so many things. We hear so many things. If our brain were to store everything, our brain would like explode, right? There's so many things to take in. So our brain has evolved to only take in the things we care about, we think is relevant. Does that make sense? And that makes sense. Like, I think everyone can attend to that, right? Like, if you let's say you have a really fun birthday party, you have such good memories for that. You're gonna remember that, right? But then if I ask you, what'd you do the day after the day after the birthday party, are you gonna remember that? Probably not, right? You will. Or is it because the birthday party is significant? Let's just say like,
No,
what's
just continue. Just forget after that.
what's a really good memory, or like what's something you remember really clearly that you're willing to share?
Going to Bangkok.
Going to Bangkok. Do you remember what you did that week after when you came back?
The week after.
Yeah.
We just rested. We just stayed at home.
Well, do you remember exactly like?
Okay. We came back. We put on luggage.
You're just trying to.
I jumped on my bed and fell asleep for like 2 hours. And then
What about the day after that?
Okay, I don't know.
Yeah, but that's because it's not significant to you. Maybe the day you came back significant because you remember that. But do you get my point? I know I'm like being a bit annoying, but like, see, the point I'm trying to make here is that our brain stores things by significance, and like there's no such thing as like. Yes, your word. Yes.
Okay. No.
There's no such thing as like our brain doesn't change when we study. You can't just be like, okay, let me just try to put cram all this information into our head. No, you gotta put fake connections there. Because at the end of the day, a lot of this stuff is abstract. You don't really like relate to it on a daily basis. So that's why you should try to fake connections as much as you can. So actually, what memory is importance if we think it's important to us, right?
Okay, I remember
You just got a crazy memory, maybe. Importance. That's the first thing. So if you think it's important, we store it. But then if things are connected, even if it's not important, we remember it. Those are the two things we got. There's a few other things, but these are the two most important things. We store things, store information based on how important it is, and also how many connections it has to it. So even if something's not super important, if it's connected to a lot of things, yeah, then you can probably say it's something you can remember, right? And an example of this is think back to caveman times, right? What's our goal? what's your goal if you're caveman? You're trying to
eat, survive,
right? So let's say you go and you see a berry on the ground. Never seen it before. So you have no like previous knowledge of this. But you've seen all these other poisonous berries before that look very similar to it. What do you think the caveman's gonna do?
Eat it. I mean, it's caveman.
Cavemen aren't dumb just because they didn't study.
Then, I mean, why do people refer to other people as like, oh, you're being a caveman?
But that's just like a stereotype.
Okay, then.
But they will.
Okay,
It's not like they're gonna get offended. It's not like they're gonna get offended.
No, but like it's not the point though, right?
They will leave it.
They'll leave it, right? I mean, like that's what they're built to do. Instinct is going to tell them to leave it, right? Or maybe some of them are like a bit crazy, but then they die, and then natural selection means that they didn't survive out. So those dumb cavemen don't survive out for too long.
A lot of villains in like movies and shows.
What do you mean?
They just choose natural selection over anything.
Oh yeah.
The weak and the strong.
True. Yeah, I'm not saying like I don't think it's the best thing. I don't know. Let's not get into natural selection now. Like, trying to justify that. Yeah.
It's like 10, 16.
Yeah, but it's fine. Like I think the point is the two facts, right? But the point for that caveman story was that because even though it's not really super important, he had connections to other knowledge that he knows, and then he used that to not eat the berry, right? Maybe but then the ones who
Okay, we get it.
Once you ate the berry, they're not here anymore. So they're not ancestors. But so we're ancestors of the people who didn't eat the berry, right? So right. So we're trying to make connections as much as possible. But what does this mean for you? Is well, whenever I'm teaching concepts, you should try to think about what problem does this apply to in real life, and then if then you can find some importance, right? And the second thing is try to connect information. That means connect to things you already know and connect to things I teach you today as well. Those are the two things. Make sense? I know I've thrown out the story, but there's two key takeaways. So focus on that for the rest of the lesson. Cool? Okay. But anyway, back to number bases. Right? So basically, what our number system currently is well, each digit has a place in base 10 of this one's 1, the next one's 10, the next one's
11. Wait, in base 10?
Yeah.
100,
which is 10 squared, right? And 1,000, which is 10 cubed, and so on. What any other base is just switching it up, being like, okay, well, actually, no. Do you know why it's 1, 10, 100, and 1,000?
Number of value.
Well, why is it that?
Because so I hate saying basically when we're doing bases. It's the ones value, then the tens value, then the hundreds value, then the thousands value, right? Depending on which place value it is, so we have the ones value, right? Which would be like 10 to the power of 0, right? Because it's the first one, we don't count that.
Yeah.
Then when we get to the tens, we do 10 to the power of 1, which would be like...
Oh, yeah, okay. No, but that's just the algebra band. But why is it 10? Why is it 100?
Because of the...
It's to adjust to that certain base.
Yeah, essentially. Well, in base 10, we have 10 unique digits, right? 0, 1, 2, 3, 4, blah, 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 until 9. But then at 9, we run out of digits. So we create a 10th one. 10th one, we use the digits we have, and we just start with 1, 0. That's where this place comes in. We reset back to 0 on the units, but then we add a new place and make that have a value of 1 more than the previous number. And then we keep 30. But then we have 99 at some point, right? And basically that means we've used 9 of this and 9 of this. And that means next one's going to be 100.
So is this how the Hindu Arabic numerals came from?
I'm not exactly sure, but maybe
it's taught earlier.
Number basis, because it's different. I think number basis is not taught in the curriculum.
Okay.
A lot of the time. We might get a basic idea of it, but I think it's useful. I think having a good understanding of numbers is super important. But do you understand like how this system formed, right? And essentially, well, now all of a sudden, computer scientists in the 1930s, they go, oh, well, we want to work in base 2 for computers. They realized they can use like on and off buttons to simulate. What's funny? I don't know how to do on and off, but you can turn numbers like it's a switch. Literally, computers back in the day were literally just switches, and each switch was like a 0 or 1. So they were like, oh well, I can. They modeled computers as binary numbers. So they wanted to work in a number-based system of 2. Then they realized, well, if you have only 2 numbers, I run out of digits at here, just at 2, and then I create a 10, but then 11, but then I run out of digits even here.
Okay.
Then I get to 100. That's 4.
And you get to 101.
Yeah, and 101, and so on. But then just sort of repeats, right? And essentially, you get this place values being 1, 2, 4, 8, 16. But then, people who because of this, they developed the theory of number bases. And then they were like, well, we can apply this to base 3, base 4, base 5, base 6. They might not be that useful, but mathematicians like to explore that sort of thing, right? Don't ask why. They just do. Like, they've solved the problems that are super, irrelevant to us, but they just like it, so they just solve it. But they extended it to any number because the logic would apply to anything, right? So if you go to base, they're like, well, what if we had 4 digits now? 0, 1, 2, 3. You need a new digit at 1, 0, which is 4. So they gave 10 the value of, the 10's unit value of 4. And the 4 is in base 10, by the way.
Mm-hmm.
Right? We're always relating it back to base 10 because that's just how we think. And then they're like, well, this repeats for 20. So you get another 4 here. Then to 30, another 4. And then you get to 40, which is another 4. It's like 16, right? Do you see how you have 4 sets of 4? So it's 16. But you can't have 40. It doesn't make sense. Why? Because 4 doesn't exist in this space. So what do you do?
1. Make it 1, 0.
1, 0, 0. Now it's 100 4 squared. Because you have 4 sets of 4. Does that picture make more sense? Why it's go from 4 to 4 squared? I think that might be the one I'm trying to explain clearly a bit more. And then you have 4 sets of these when you go back to 1,000. So you have 100, another set of 16 is a 200s, another set of 16 to 300, and then another set of 16 to 400. But then you don't have 400, so what do you do? 1,000.
Yeah.
Make sense?
Okay. Next.
Yeah. 256.
Wait.
This is 4 cubed.
Okay, yeah.
Which is 64. The next one is 256. But, not 39, 33 actually. It stops at 3. Right? And that is how the logic of number base is formed. Okay, now we'll come back to the example. All right, so base 16 to base 10. So you have 3, 1, 2 in base 16.
Mm-hmm.
Oh, by the way, any questions? You should have questions. If I say, do you have any questions? And then don't think it's good that you don't have questions. You might think, oh, I understand it. I don't have questions. Ask questions.
I understand.
You're all beginners to this. You just learned this today, right? Let go of the ego and be like, oh, if it just ask questions, force yourself to ask questions. And that is how you maximize learning. Okay? So anything you're slightly even curious about, yeah. Come on, guys. If you give it a go, it'll benefit you. Good. Did that visual make a bit more sense? Because I think that shows how you go from 4 to 16, right? And then you have another set of literally those numbers 4 times. From the 0s, the 100s, the 200s, the 300s, but then the 400, what do you do there? So you come up with a new number, basically. And do you see how it just goes forever? Yeah. So that's why it multiplies by 4. It just sets of 4. Anyway, let's see. 312 by 16. Oh yeah, so we're in base 16 now. So based on base 16, based on the theory we just learned, What do you think is the place value of each of these?
Ones, tens.
This is base 16.
Okay. Place value of those.
You know what? Since you didn't have any questions, I'm assuming you're all good with everything here. So tell me, what is the basis here? You can give me like the powers. You can calculate afterwards. What do you think this is?
Base 16 to what?
So no, I just want to tell you to tell me what the place values here are.
1, 2 to the power, 16 to the power 1, and then 16 to the power 2. That's what you meant. Okay.
Yeah.
I was like, what is
Sorry, my bad. Yeah. So what I meant was, what's the place values for each of
Okay,
these?
yeah.
Yeah. You got it? That means you got it, right? And well, so that means if I wanted to convert this to base 10, I just go, I have how many ones? 2. Plus how many 16s? 16 times 1. Plus how many 16 squared?
16. Wait. Could you repeat what you just said?
How many 16 squared? That's this 3. That's just this base, this number.
Oh, yeah.
300 just means 3 of those.
Yeah.
Makes sense?
I was just getting sidetracked.
And then you just add them.
256.
You don't have to do this in your head. You can do this.
No, I just said you say it randomly.
Yeah, no, but I'm just saying, like, if you're doing it, like, without me, feel free to use calculator. I mean, feel free to use the what is the word for it?
Right?
750 plus
What's the gap?
Yes, working out. Okay, forgot English. Yes, thank you.
759 plus 16 plus 2, 16 plus 2, 18. So 759 plus 18.
It's even.
Yeah, I'm just thinking 759.
759 is close, but not it.
Isn't it? 3 times. Oh, it's 3 times 6. My bad. I was doing 3 plus 3 times 6 is 8. Oh, God. I'm not consistent.
768. Yes, agreed.
768.
That's just the 3 times 3, 256 part.
6.
I mean, I'm gonna let you do the calculation. This is arithmetic, right? Yeah, you can do this, but the point is, you know how to do this, right? So just continue that on. You should get 16 here, 2 here.
So 786.
786, yeah.
Oops.
Cool. Does that make sense to everyone? It's just arithmetic. If you didn't get to it, just finish the arithmetic. But the key idea is the initial bit, where you need to think about the place values. This is the problem solving bit, right? Then we get to 786 in base 16, sorry. Cool.
Wait, wasn't that already in base 16?
So sorry, it's a,
312, like, wasn't.
this is base 10 number. So.
Oh, okay, yeah.
Yeah. So it's 786 in base 10. Make sense? Sorry, I just misspoke there. But 786 is in base 10. Does that conversion make sense? Now, what if we wanted to convert this to base 2? Because we wanted a computer to use it.
So then you do the same thing you just did, except like you do 1 and then 2 to the power 2 to the power 3 to the power 4.
Yeah.
Right.
But it's not the same thing because you're reversing it. But like you're using the same logic.
Yeah, same logic. Good.
Yep, exactly. Yeah, well done. Now the question is different, right? Because like we can write, 1, 10, 10 squared. Not super relevant to us because we already think in base 10 enough, right? We don't need to like think about it like this. What we want is to convert this into the different base. Right? Convert this to base 2. And what you need to realize is base 2, the value of that digit in that. Wait, give me a second. Why don't you think about that? Okay, yeah. The value of the digits in base 2, right?
Okay, so it's 2 to the power 9.
Yeah, that's the highest you go. But then each digit. Let's say this digit's 1, this digit's 2. Next, what's the next digit in base 2?
2 to the power 2.
To the power 2.
That's one. That's one.
But it goes up forever, right? Go 2 cube, 2, 4, 2, 5, 2, 6, 2, 7, 2, 8.
Yeah.
You can get as big as you want. How do you know when to stop?
When like the number is, I don't know exactly how to explain it, but say if like 2 to the power 9, right? That's 512, right? Yeah, 512. 786 is bigger than 512, but then what's the next? 2 to the power 10, right?
1024.
1024. Yeah, you can see that 1024 is bigger than 786. That means you would just be putting a 0 there, and it would just start with 1.
Yeah. Okay.
Like, do you get where I'm going with
No.
this?
Yeah, I definitely agree. Yeah.
Because
this is
just think of this.
No, exactly. It's the same logic, right? It's with a big number. The first thing is you can think about how many digits there are, and that is literally going up until this power is bigger than this number. So 2 to the 5, that's 32. 2 to the 6 is 64, still smaller. Is 128. It's getting pretty big, but we were nearly done, right? 2 to the 8, it's 256. 2 to the 9, yeah, 512. Makes sense so far?
512. How can it be 2 to the power 8 is 256? And, 512, my bad.
Yeah.
Never mind.
2 to the 10 is
1024.
1024. But then you actually, I know you went until we got too big, but you don't need this digit because 1024 is too big.
Because you're trying to divide. No, see how many numbers can fit into the.
Yeah, exactly. You're trying to see you're trying to see how many 786s go into each of these digits.
You mean like 512 going to 786?
Yeah. Okay. Yeah. My bad. I've been phrasing things in reverse the whole day. How many of these digits? Sorry. How many of these digits go into the big number? Yeah, the 786. Right? Well, there's 1024 is too big, so no 1024s will go into 786. So you'll never need that digit. But what we will need is these digits. And what you do is you basically go, okay, well, how many 512s go into 786? 1. That means you've used that digit, right? Now we have 512 already. So we're going to take the remainder with 512. So we need to do 786 over minus 512. What do you get?
274.
274. Now we work with this number. So I'll write down the number we work with here. We work with 786 here, but then when we get to here, we only work with 274. How many 274s go into 256?
1.
1. Right? And then now what's the new number? I've sort of put 1 in here, so I've got a remainder I've got to work with.
18.
18. So it's 18 now.
It's 0.
How many 18s go into 128?
You mean how many 128s go into 18? Right?
Yes. Yes, sorry. I keep getting it wrong. Yes. How many 128 go into 18?
0.
0.
And then 0 for the next one.
So because of that, the remainder is still going to stay at 18 because 0, the remainder is going to be 18. How many, let me see if I get it right. How many 64s go into 18?
0.
0, right? And you just keep going 0 for a little bit. How far do you go with 0? Do you have 0 here? What about here? What about here? Oh, sorry. 2 to the 4 is equal to what?
16.
16.
So,
do you have a 0 there? If it's 16? No. Why? It's 18. It's bigger. How many 16s are in 18? 1. Right?
And then it's 2.
0 all the way until 2.
Yeah, so now it's 2. So 2 keeps going for a little bit. And then you get to here. Oh, well, look. 2 and 2. Perfect. 1.
Oh, yeah.
And then the remainder is going to be 0. So there's 0 ones as well. Cool?
110001001.
So I was literally doing this in my head.
Yeah, that's not.
Yeah. I just went, oh, that's 1512. The remainder is 274. That's 1256. Now I'm working with 18. No 128, no 64, no 32. 16, there's one of them.
You got a PlayStation 5 and the first question you asked was.
Oh, why is your name 2 to the power of 10? The username. Because my friend's username was something 1024. That was their birthday. I just thought 2 to the 10. But yeah. But like, do you see how you can? I'm not expecting you to be as fast as me. But the point is, you can, if you have 5 minutes, you probably think you can do this algorithm, right? Okay, now my question for you is, can you convert this to base 3? And I want you to, yeah, I want you to do it.
So that number, the 1100010010, that one, it's base 3.
But I want you to do 786. It's easier to start from 786. Convert 786 in base 10 to base 3. Use the same exact logic I did, right? Think about the placeholder values. Go up
It's going to take forever.
Calculator allowed for this.
Everything.
No phone allowed though. You can't be like, oh, let me use number-based converter. Oh, my phone, my calculator's in my phone.
That is so good.
Do you think, like, I want you to care about this topic a little bit. Is what I mean by this. Like, instead of just thinking of it as like, oh, I need to learn this for school. I want you to think of it as something relevant to you. Yeah, but I know it is. It is at the end of the day, it is for school, right? But it's more efficient to think of it for other purposes. Because if you try to just rote learn, your brain will not give a shit. It won't. It just won't. Think about this. You remember, you guys play video games, right? You remember things for your video games more than you do for school. Why? Because it's relevant to you. You like it. You enjoy it. Add some relevance to what you learn. Think about this. This is like this. People, when people came up with this was relevant to them. That's why they did this. So you might think like this guy who came up with it's a nerd, but he loved it, right? That's why it was like playing video games with him, probably.
Wait, for base 3, do you still put 1 here? 1 here?
The unit's always 1.
Yeah, 1 there. But then it goes to 3. Then 3 to power 2.
Then it's to 3 to power 6.
Don't give it away.
He's using a calculator.
It's fine.
But you're allowed to use a calculator.
I said you can use calculator.
But it's in the phone.
Because you have a converter online.
Yeah.
The calculator is not a converter. Do you have a calculator?
Here, you can just use my one. I'll use the calculator on my phone.
Okay. Yeah, I trust you. I trust you. Don't worry, I know you're trustworthy. I was just joking. Because you found the calculator. I found the converter
Yeah,
online.
you found the converter.
Yeah.
But thanks for 3 power 6.
But you gotta get everything in between as well. And afterwards, we'll go to your method, Tanuki. That also works.
Wait, how do you? Oh, yeah.
That's it. That's it.
I'll take a look. It looks good. Let me just confirm. Yeah. Well done.
Is there ever gonna be a 3 in this answer? A 2 in this answer?
Yes, there will be.
Is it in the first 4 digits? Okay. So no then. Okay, so no. Thank you.
We should I think you should be confident enough without that. You'll be fine. You're doing well.
Yeah, I know.
Yeah. And also, good thing to check is if you get a digit like 3 or more in your base 3 answer, you're like, I've done something wrong here, and check your work, right?
It started looking like binary, so something. Wait, is there a K for just ones and zeros?
Yeah, there's a number 100. The number 101 exists in base 10 as well. You just can't exceed. No, I think if you had 759 as your number, everything will be only ones and zeros.
Okay, so
and that's okay to happen.
Okay, is this the answer?
Close.
What do you mean close?
What's the remainder?
You hear me?
After 27, after the 57, what's the remainder? Ultimately, though, I want you to be able to do this without a calculator as well.
Yeah, so
which is a bit unreasonable, I know, but yeah. The reason is, well, if you go into do any sort of math competitions,
they won't let you.
Yeah, and but the thing is, all of the questions in the math competitions, you might need to do base conversions without a calculator.
Without mental
you can still
yeah, right working, that's fine. Yeah. But now I think you know, right? You can just do the calculation a bit slower on hand, by hand.
Would that be a time limit?
You got plenty of time in most math comps. Like for instance, the one I did in year 7, it's called AIMO, Australia Intermediate Maths Olympiad. You have 10 problems. How long do you think you have?
Wait, repeat all of that again.
So I did this Maths Olympiad in year 7. 10 problems.
Okay.
How long do you think I was given?
1 hour.
2 hours.
4 hours.
How long did you
God damn!
First time I did it, I only got 4 questions right.
How long did you take?
That's too smart.
The whole time.
That is too smart if you get 4 questions right.
Can you show one of the questions if you remember?
I got plenty of them stored on my computer. Like a nerd. I got 2017 paper. This is a paper.
2017.
That's one I did. That's hey.
I'm not saying it's cool, but I'm just saying you had papers since 2017.
No, I got it later, but
Okay. I was like, what?
Are they calling me 2017?
No.
I was in prep back then. What were you in?
I was 6. Yeah.
You're probably prep, right? Damn, I got that right. I can't believe that. Yeah. Oh, look, first question, literally number-based question.
The number x is 111. Okay. Written in base b, but it is 201 written in base b minus 2 x in base. Hell no.
No, we don't know the base yet. Base is b.
It's all letters.
Yeah. The base is all those letters. This is question 1. This is the easiest one.
Yes, 7, right?
Yeah. But it's math competition. It's harder than school. It's a lot harder than school. But I recommend trying to participate in them. It'll make you like maths more.
It will make me like maths more.
Yes.
By doing harder questions.
If you like that. I like that.
What you got wrong?
I got most of them wrong. I got 1, 2, I think. Took a long time. I got 4, I think.
But they still give you 4 hours.
I think I did 1, 2, 3, 4, and I didn't get 5 onwards.
What's 10? 10 dig is a game for 2 players. They try to make a 10-digit number with all its, I can't read the last one. Digits different. All its digits.
It's a game.
That's not a game. That's a maths question.
But you're playing a game. You're trying to find the strategy for the game.
Oh, hey guys, let's play a game called 10 Dig.
What's
You
that?
want to know what it is? We have to try and make a 10-digit number with all its digits different.
So but you're gonna make fun of 24 as well. Then the same thing. The maths game.
Yeah, but that one's fun. It's just multiplication, addition, subtraction.
Oh, so it's easy. But
Yeah,
it's no fun if it's too easy.
Okay.
Okay. Anyway,
you're
we're getting
competing.
sidetracked. Yeah, but you're competing against other people here as well.
Yeah, that's different. This one has like 10 questions that are
All right. How'd you go, Nikki? Sorry, got sidetracked. Think about the remainder. Yeah. Up to 59. What's the remainder? 57. Carry the 57 on. So you have 0, 0, 0. Yeah. Oh yeah, here. 57, 27. How many are there? How many 27s are in 57? Two. Not. After that, it's
So do I just write two?
two. Yeah, two. But then, what's the remainder now? Three.
Hey, Luca, here's a fun maths question for you.
Yes.
If 1 equals 3, 2 equals 3, 3 equals 5, 4 equals 4, 5 equals 4, then 6 equals
1 is 3, 2 is 3, 3 is 5, 4 is 4, 5 is what?
4. Then 6.
Let's do it up. Let's do it up.
No, it's a really simple one, I promise. It's like a,
I don't know.
the answer's 3.
Why?
Letters. The letters 6.
Oh, the number of digits. Number of
digits your letters? That's
number of oh my god, number of letters in the word. Okay.
That's nuts. He's making everything nuts.
Yeah, well done. Now you get the logic, right? All right. All right, next way to do it. This move. No. Cool. Next way to do it. This is actually the Nuki's way. So I sold it off her, but this is quite cool, I think. This is actually faster, but I think it doesn't really get... The reason I prefer the first way to teach you initially is because the other method makes you think about the number construction, but here it doesn't. It's just a shortcut way to do it. So let's say you have 786 in base 10 and you want to convert to base 3. I'm sure all of you got 1, 0, 0, 1. No, sorry, 2.
No, isn't it 1, 0, 0?
Sorry, my thing is just cooking me.
The brain?
No, I've got like a little workplace. It's not moving. Do you see it? Oh, yeah, it's stuck in the corner.
0, 2, 0, 0.
Sorry.
2,
Cannot
1,
move
0,
this.
0, 2, 0, 1, 0.
Please move.
It's kind of...
It's like, do you see how it's partially there? It's stuck in the corner. I can't grab it. I have to just make do with... Now it's completely messed something up.
Control C.
Okay, it's working now. See, I wish I could.
Wait, no, Control Z, not Control C.
It's iPad though.
Yeah, but like functional control.
So you got 1, 0, 0, 243, 81, 2, 0, 1, 0. Yeah, okay. There's another way to do this. We won't have time to go over the logic of it, but if you think it's faster, try it then. I'll go over the logic of it next week. Oh my god. I don't like this. I can't change color.
8 minus 7, that gives you 1.
Okay. Just bear with me with these terrible colors. I just can't switch because of this thing broken. What you can do is you can divide by the number by 3. And what does this give you?
There's no way that works, right?
Oh, sorry, you want the remainder. You don't care about... Oh, no, you do care about the number. If you divide this by 3.
Okay, so 2, 6, 3.
2, 6, 2.
Oh, yeah, it's my bad.
Remainder 0. Now, this remainder is our first thing we care about. Why do we care about this remainder? Because that is our units digit.
Oh, what?
Units digit, like the 1 digit,
Okay, yeah.
is 0.
So that's
Why though? Why do you think that is?
Because we divided by 3.
Yeah, think about this. All these digits afterwards are multiples of 3, right? So the remainder when you divide by 3 is literally whatever this is. Makes
The
sense?
remainder you divided by 3. The ones, okay.
Makes sense? It's like, dividing 786 divided by 10. What's the remainder?
786 divided by 10 is 78.6.
Remainder? 6. Just the digit, unit digit.
Okay.
Yeah, any number, you divide by 10. Because we think base 10, right? In base 10, whenever we divide a number by 10, the remainder is whatever the ones digit is.
Okay.
Yeah? So, same thing here. Same logic here, but in base 3. And then, now you think of this as your new number, 262, and you divide it by 3 again. Yeah? Then you get, what's your number here? You get to do a bunch of long divisions.
13. 100. Wait. 130. No, 13 remainder 2.
I don't
Oh,
think
no,
so.
that's way off.
It's like 80 something.
Sorry.
Do it on your 8, 24, 2, 2,
Oh, wait. That doesn't
7, 87, 120. I think you did 362.
Oh, you didn't even have to just
120 times 3. But anyway, it's 87. Remainder 1. Okay. And basically, this new remainder is our 10th digit. Why?
There's no way this works, right? This
Because think about it. You sort of divide it
so
by.
you just divide the base with the remainder,
Well, you've sort of like.
like whatever the number is given in the question, you just divide it by the base that you have to transfer it into.
Yeah, and just keep doing it, and you take the remainder.
Okay, and then we still get the same answer.
Sort of. Let me know. I'll 87 remainder 1. Oh my god.
Wait, that doesn't work.
Oh wait, sorry. This works in reverse. No.
This doesn't work. You got the first 2 digits right, but then it can't
Yeah,
be
it doesn't
1
work.
there,
Yeah,
it
no.
has to be
I
0.
realized. I think it's other way, right? Yeah, other way. Sorry. Wait, what did I do wrong
How
here?
can it be other way?
Yeah, other way also doesn't make sense.
Yeah, that means it just.
Wait,
How
I've forgotten
does
this.
How does this work?
First one makes sense.
When the teacher forgets maths.
Look it up online.
Hey.
No, okay, no, it does work. It does work. It does work, yeah. It's a remainder you carry over.
Yeah, that's what we've been doing, right? We're carrying over the remainder.
So,
Starts at the last. Like you've done remainder 0 and you put it in.
so the rightmost, right?
Like the down is like the first.
The down. This is the
It starts like you do it and then the remainder starts at the bottom and then goes on.
Yeah, okay, that makes sense. But that's the sort of like backward. Yeah, okay. Yeah, okay. It makes sense. I think yeah, there's no mistake here. So you get 1 here.
Yeah. And then see we have a remainder 1.
Okay, then you go 87 divided by 3.
But what happened to the 1 over there? You're just forgetting about that.
This one.
Yeah.
Put it in here.
No. Oh wait. Oh yeah, my bad.
Now you have this number left over. 87 divided by 3 is 29. Remainder 0. So you put a 0 here.
Mhm.
Then you get 2. 29 divided by 3 is?
We have a remainder 2.
9 remainder 2. Yeah. 9 divided by 3?
3.
3 remainder 0. That's going to be here.
Mm-hmm.
Well, 0. And you have 3 divided by 3.
1.
1 remainder?
0.
0. So you put another 0.
And then you have 1 0.
1 divided by 3 is? 0.
Mhm.
Remainder 1. 1. Same number.
That is not how the logic works.
The logic is remainder, basically. I mean, think about this. In base 10, I'll give you a really big number.
Mm-hmm.
This is going to be a completely useless thing to do. But I could construct this in base 10, which we already know, but you can construct it in the same way, right? You do 7263, divide that by 10. It's 726. The remainder is 3. Then you go 726 divided by 10. It's what?
6.
But 72, remainder 6. 6. 72 divided by 10. 7, remainder 2.
So you just
I get the same number, but I just keep doing this. It's pointless. But it's the exact same logic.
what was the point of that?
But it's the exact same logic
Yeah.
when you go to base 3. 7263 is
The fact that we
7263.
understand this shows that- oh my god. We're laughing over a math question.
No, but the point though is that but here's what the similarity is, right? Now we're working with this as a new number and trying to construct it from here. We pretend this is the units now, right? So we're trying to find what 262 is in base 3, but then we only consider these digits. Well, the unit digit's got to be the remainder when you divide by 3. That's the unit that's here, though. Do you see we shift the units up by 1? Does that logic make sense? And then we can do it like that. Is that do you have any questions from that?
No.
You should ask questions.
Actually, I have one question.
Yeah.
Why did we just do that example? That was just so fun.
But I'm trying to show you the connection.
Yeah, you're gonna give us like a different number with a different base then.
But then it's harder to see the connection. Because we think in base 10. Do you see how this makes sense to us, right?
Yeah, okay.
It's the exact same logic in base 3. But it's just harder to see it because we don't think in base 3.
Alright.
But do you see that's a good question to ask.
That was just
It seems pointless. It seems pointless. It is pointless.
You're just getting the same thing.
I was like, oh wow, 7263 is 7263. Yeah.
Someone wrote in binary.
So
Oh my god.
Stop.
So
We're,
it's like
we're not gonna bring this up again.
the base. What if you call it base 6?
Yeah. But
This guy has weird thoughts.
that's the second. Everyone has that. People who have weird thoughts are that's good to have. Yeah.
That'd be a great coder. Or someone who'd be great at computers. Just always thinking in binary.
Oh, he's a computer. What if you like
Oh my god, this is good.
you have like a kid and you just train him up to just think in base 2?
So what? When you're gonna buy a copy, you walk in. Hi, how much would this cost?
I mean, they could
1011.
Yeah.
They'll be like, I'm
Oh.
sorry, Google Translate, please.
Wait, it's 1-1. Oh, it was I prefer 1-0.
Computer or like cashier.
Yeah. Oh no.
Then you can just like voice command.
This is all right. Anyway, have we run out of time? Yeah, we have. We'll stop it there. Today we just covered number-based conversions. So I'll put a few extra practice questions for number-based conversions.
Alright, but like you know how last week you said that we'd be doing that thing that we'd be switching the things
Yeah.
around?
We're gonna do that after actually. So the new way it's gonna work is once we've all covered all the content.
Are we gonna do arithmetic next then?
Yeah, we're actually gonna come back to something else, which is in number theory basics, which is finding greatest common factor and highest common
LCM and HCM.
with prime factorization.
Are we gonna do Euclidean algorithm?
We can. Let's do it.
I forgot how to do Euclidean.
Yeah. All right, let's do
I
it. Let's do it next
remember
week.
how to do prime factorization.
Do you guys like today's lesson?
Yeah.
It was a bit sidetracked though.
Yeah, that's
The
fine.
caveman. What if the caveman ate the berries?
No, but I want you to try to make as many connections.
Yeah.
So that's why, if you care about this topic more, you will automatically, naturally want to learn it more, and you naturally be better. So, if you get sidetracked, being sidetracked is part of that discovery process, right? Because by being sidetracked like that, not the caveman stuff, but like with all these other questions about computer science stuff, that gives us purpose to learning this. Because otherwise, it's just a pointless thing you learn to school. Right. So I recommend when you're studying at home, try to learn about why we're learning this topic, and also try to make connections. Do you see how we connect? This is a connection. Do you see the connection I made? When I did this pointless problem here, converting 7263 in base 10 to 7263 in base 10, right? The point though is when we connect these two concepts, hopefully it'll make a little bit more sense to you, because they're naturally hard things to learn. But if you form connections, you can leverage these connections to understand it better. Okay. Do you want to do Kahoot, or do you want to head off?
You guys choose. I don't really care. It looks like you guys just want to head up.
Yeah, how my head up.
Look, I have one question. Look, what is the number of parking space covered by the car?
I've seen this before.
What's the answer?
It's upside down.
No, it isn't. Is it?
87.
That is okay. Even I didn't understand that. So. Okay. I am an odd number. Take away one letter and I become even.
I mean, if you want to do Kahoot, I'm happy to do Kahoot. It's okay. Do you want to head?
I'm going to myself.
Hey,
So, do you want to do Kahoot?
I mean, it would just be me versus. I don't think it's really worth it. There's only 3 people.
Yeah, okay. Yeah, it was a bigger group.
I have one more question.
Okay, yeah.
I'm an odd number. Take away one letter and I become even. What am I? That's why you left me with I'll tell you, it's between 1 and 10.
Odd number.
Yeah, 7.
That's even.
Oh.
Okay.
I was thinking of 11, but then you take 2 letters away to get even. That's fine.
Okay, wait.
Cool. If you want to go, you can leave.
Yeah,
It's fine.
okay.
But like,
I just have one question for you, just specifically.
Okay.
Sally is 54 years old, and her mother is 80. How many years ago was Sally's mother times her age?
Wait, what?
Sally is 54 years old,
Yep.
and her mother is 80. How many years ago was Sally's mother times her age?
Times her age.
Yeah.
Twice, you mean? Not.
How many years ago was Sally's mother times her age? Just says that.
Sally's mother times her age. What the hell does that mean? That's really it. What is it? Times her age.
Do you want me to tell you the answer?
Yeah, tell me.
Okay, 41 years ago. I don't get it. It says
13.
41 years ago when Sally was
Thrice,
13.
I think. They spelled it wrong.
How many years ago was it? Doesn't say thrice. Yeah.
That's 339.
Yeah.
I think it's just thrice, maybe.
Okay, last one. There's a 3-digit number. The second digit is 4 times as big as the third digit, while the first digit is 3 less than the second digit.
Sorry, give me a second. I forgot this spelling.
Huh?
Like
Or you like your teacher?
Huh?
You like your teacher right now?
Yeah.
Is that why you're not sure you want to switch?
No. So no. So like, because we had that old deaf like teacher,
Okay.
I didn't know how I was doing.
Oh, okay.
Yeah, like I couldn't tell if I was like doing well in it or